scalar or a vector depending on how they are multiplied. Thus, there are two types of vector multiplication. Scalar product or vector product. Scalar product is expressed as A vector dot B vector. So you would write something like A vector dot B vector. This is the scalar product, or what we also call dot product. The other one is the one we are calling vector product. You say A cross B. Why I'm writing this is because sometimes I write and I write with something that might not be clear. This is an arrow. Always remember to write to draw the arrows on top of a vector whenever you are writing, because you are not going to have the privilege of typing most of the concepts that we are doing. So you are doing hard writing. Therefore, when you hard write, you put the arrow at the top. If you are dealing with a unit vector, you put a heart. So these are the two concepts of multiplication. But then you also find that concept that combines dot and cross, such that you have three vectors A, B, and C, and you might require to get a scalar triple product. And a scalar triple product involves U dot A with the product of B cross C. You don't say times. Remember, you don't say times. But when you are dealing with vectors, we say B cross C. And you always remember to put the arrow on top. So what we'll know is that of course, we are getting there shortly, that the product of a cross product, or the output of a cross product, is another vector. But the output of a dot product is a what? Is a scalar. So these are very important concepts that you must get, because you might get lost if you miss out on those basics. Now, the last concept is vector triple product, that you have a vector A, you are crossing with vector B cross vector C. And we will try to find out if this multiplication laws follow the rules of association, commutation, and distribution. And we'll see that they do not necessarily follow, as we found out in the addition and subtraction. So we are going to be looking at distribution laws, whether the multiplication of vectors follows that, or whether the multiplication follows the association and the commutation. So we start with the first one, dot product. A pause would be good. Let me take a glass, and if you have any question before we go there, you can ask. I'm giving members to grab a cup or a glass of water. Where are these controls now? I need to push myself a little. So I'm waiting for any question or any comment before we move on. Meanwhile, I'm taking a glass. Can't see my. No. Okay, I'm back. So can we carry on? Yes, yes. So let's talk about the dot product. And the dot product of two vectors written as such is defined geometrically as the product of magnitudes of A and B and the cosine of the smaller angle between them when they are drawn tail to tail. That is the definition or geometrical definition of dot product. So question 115 is the definition. You get the scalar or the magnitude of A, magnitude of B, and then you multiply with the cos theta, which is the angle between them. So here is the idea that you have a vector that this is head and this is tail of vector A. And this is vector B, head, tail, and this is B. The angle between them, tail to tail, is theta, A, B. So if you wanted to find the dot product of A and B, this becomes the dot product of that. I believe that is clear. So I have explained where theta AB is smaller AB than, I can't see the shared screen. Oh no. Okay, thank you, Ashuka. I think I had muted, I had paused instead of muting myself, so that is the cause of my trouble. So I think now you can see. I was going through this idea that this is vector A has tail on this or behind where there is the arrow, that is the head, and vector B where there is the arrow, there is a head. So you join them tail to tail. And the angle between them, that is angle theta B. And what you actually end up having is that A dot B is equal to magnitude of A, magnitude of B, cos theta AB. Now, the result of dot product, as I mentioned, is what? Is a scalar. I mentioned that because it is a scalar product because it is scalar, or the dot product due to the dot sign. So what we just need to know is that the output or the result of dot product is always a scalar. It doesn't have a vector. So like if I give you AX, or vector A is equals to 2AX, and vector B is equals to 3AX. Okay, so if you wanted to find the dot product of A dot B, this would be equals to 2 times 3, and AX dot AX is actually a 1. I started hanging this one now again. It becomes this product of AX dot AX is equivalent to 1, and therefore the answer becomes 6. Therefore, this is scalar, doesn't have any direction. All right. And moving on, so we are saying this is how it looks like if you had the three terms. I've just given you an example with only AX term because the unit vectors actually go away or they diminish because AX dot AX is equals to 1, AY dot BY unit vectors becomes to 1. Therefore, you are only left with this as scalars, and you add scalars directly. So we want to find out if the rules that we mentioned earlier are You want to find out if the dot product follows the commutative laws and the other rules I mentioned. And before we do that, we are going to say that two vectors A and B are said to be orthogonal with each other if the dot product is equals to 0. What does that mean? Orthogonal means that they are perpendicular to each other. So this is A and this is B. So if these two vectors, the angle between them is 90, that means cos of 90 is always 0. That means that these two vectors are said to be orthogonal. This is a very important term. You should write it somewhere because you find a lot of its use in engineering. Sometimes you hear it's orthogonal, you don't know what orthogonal means, and therefore it means exactly that. That the two fields that you're talking about, or vectors, are 90 degrees out of phase. And therefore, you're saying that commutatively, the A dot B is equal to B dot A, and that is agreeable. That dot product follows the law of commutation. And the law of distribution is that if you have A dot B plus C, all these are vectors, and they don't have to have an arrow because they are bold. And therefore, we are saying that if you open that bracket, which is how we evaluate the law of distribution, it means that you're going to find A dot B plus A dot C is the same as the sum of AB plus C. Therefore, that means that it follows the law of distribution. And lastly, A dot A is equals to A squared and or the magnitude squared, and that is the other important law. And this is very important that if you have two vectors, or you have one vector and you dot it with itself, A dot A, you get its magnitude squared. So this is what this means, and that is a very significant output that you'll find its use. Now here are some laws that we apply with the vectors, and I have actually added a comment here saying that this is a very important law. In my other classes, someone called them axioms. I don't know whether we can adopt that rule, but it is very important. And here is the idea that if you have the same unit vector dotted with a different unit vector, or a unit vector in a different direction, the answer will always be 0. So if it is ay.az, az.ax, the result will always be 0. But on the other hand, if you dot a unit vector with itself, they will always give you a 1. That is what I'm saying, that these are the pretty important laws that you must observe and you must align yourself with, because they will become very useful in your day-to-day dealings with electromagnetics and even other engineering concepts. So these are axioms that you must remember. These are like, you must always sing them as a song, but they are very simple. Ax.ax is equals to 1, ay.ay is equals to 1, and az.az is equals to 1. Otherwise, anything different gives you a 0. Now, it is important. It is easy to prove the abilities above, but you don't need to do that. Just know that A dot B is equals to 0. If A dot B is equals to 0, then the two vectors are orthogonal and or perpendicular. That is the idea of orthogonality, or these 2 points being 0. That means that AX is orthogonal to AY, and AY and AZ are orthogonal, etc. All right. Any comment before we jump to cross product? Okay, no comment. So let's carry on and finish the class as soon as possible. I hope to finish. We wasted time when we had the interruptions of one that we had earlier. The cross product of two vectors A and B, written as A cross B, is a vector quantity whose magnitude is the area of a parallelogram formed by A and B as shown in figure 1.7 and is in the direction of the advance of the right-handed screw as A is turned into B. So here's the idea. I have a diagram here. The vectors A and B are indicated as such. So they are joined head to head or tail to tail. If you like me drawing, this is the direction of A, direction of B. If you had a screw now that you are tying, moving from A to B, like you are tying it like how? Like that. The direction that that screw would be going is the direction of the vector that will come out after you have crossed the product. Therefore, you are saying that vector, the output of a cross product is always a vector that is directed towards the right-hand screw when the screw is rotated towards from A to B. And therefore, if you had said that B cross A, the screw would be facing this direction, and therefore it would be going down. And therefore, you can say that A cross B is not equals to B cross A. Is that concept understood? Someone mentioned something. That is what we are defining by using so many words there. That is a parallelogram, the area of a parallelogram, and the vector is directed towards the right-handed screw as A is turned into B. No comment. So we carry on. So if you are to represent that geometrically, you'd actually get the magnitude of A, the magnitude of B, and then the sign of the angle between them. And of course, you multiply the last item. You must not forget this. The last item, which is the unit vector, that is directed towards the direction of the screw. So if we go back to our parallelogram here, we have A. The magnitude of A is that, and it is directed towards A. So it has a unit vector there. And there is a vector B has magnitude there and direction A, B, direction. So to find the cross product, which is this one, I should have cancelled that one. I wanted to say that B cross A is not equal to A cross B. So this is what I meant there. So I'm saying that A cross B is equals to the magnitude A, the magnitude B, then the sign of the angle between them, which is theta AB. So you say sine of theta AB, and then the direction of the arrow that you have determined to be AN, you put it there because this now becomes a vector. So that is important, and that is how we define that. So there's something else that we now do to represent, okay, I think I've explained the AN, normal to the not plane, and I've seen the right hard rotate, blah, blah, blah. So what we now need to do is the vector multiplication we have done at this one can actually be, is called the cross product owing to the cross sign. It is called the vector product because it is a result of a vector, and we can actually represent it as follows. We can represent it in form of a matrix multiplication, where we say that these are the directions of each coefficient, or these are the one we call coefficients, and then you are going to be doing the normal multiplication. We start with this one, and then we do cross multiply. You say A, Y, B, Z, AY, BZ minus AZ, BY, and you get coefficient of AY. Of course, when you are doing with the one for Y, we normally interchange them. So we follow the general rule of multiplying matrices. Rather, not matrices per se, but multiplying this vector or this magnitude I think the correct term to use is the magnitude. And the one that some people might have forgotten is this idea, but I can just show them very easily. We normally say that the first time we have got, but now for the second one, we normally cross this, when we cross that line, we put the AY there because it's at the center, and then we say AZBX minus AXBZ. Notice we have followed this direction first and then this one, which is only happens for the odd, this is the odd one, the even one. So AY. But when you are doing the AZ, we are going to do something different. We are going to start, this was the one, this was 2. Then if you are doing the second one, we are going to see, we're going to start with this right direction. Just see. I love that. And then I say that for the last term, I cross this one and this one. I write the term AZ. Then I say this times that. That is the first one. And then this times that. That is the second term. So you say the one is the one, and this is the 2. So that is the idea we follow. And for Y, we normally follow a different one. I don't know how I can explain it, apart from what I have showed you, that you normally, for the Y, you normally do reverse of what you are doing with the others. So that is the idea, they are different. Okay. I hope, please repeat the concept of A cross B. I've not even finished yet with age. That is what I'm explaining. Well, I can repeat. That is why we are here. A cross B, remove this idea altogether. That is asking me to repeat that. And I'm simply saying that this is A and this is B. Join them tail to tail. They make an angle theta, AB. And we are saying that A cross B is equal to the magnitude of A times magnitude of B. This is what I have here and here. Then sine of the angle there. And then the direction which the vector will have, which is that of rotating a screw from A towards B. So that means this screw is going from A towards B. It is like you are moving from A to B. So you are rotating, it is actually going facing up. If you are to do a screw and you want it to go up, it would actually face that direction. That's why I'm saying that this becomes the direction of your vector AB. That is when you're giving the arrow AN. Is that clear, Gereji? And I have just moved to representing that using the magnitude notation, which we have seen that you do the normal. I don't know if you have done. Have you? Can someone confirm this? Have you done this kind of magnitude multiplication? Thank you, Gereji. It's now clear with you. Someone confirm that. Have you done this kind of multiplication that I'm showing you here? Because you need to be sure that you can be able to do this. Okay, Brian says that you have done it.